You ever stop and think about the World Wide Web? I mean, really think about how it all works? It just feels like it's always been there, right? Like magic. But here's the thing, its success was absolutely not an accident. Turns out it was all built on this kind of secret blueprint, a plan that basically shaped the entire internet as we know it. So let's dive in and uncover that blueprint.
And the story of this blueprint? Well, it starts in a pretty weird place, with a quote from a Monty Python sketch. Seriously, it's the very first line of this super important PhD dissertation from the year 2000, written by a guy named Roy Fielding. You know the sketch? An architect gets hired to design an apartment building, and he comes back with these proud, beautiful plans for a slaughterhouse. It's completely absurd, right? But it makes this incredible point about design.
And that's exactly the point. You wouldn't try to build apartments using a slaughterhouse blueprint. It's just the wrong tool for the job. So, in the same way, you can't possibly build a system designed to connect the entire planet without having the right architectural plan from the get-go. And Fielding's dissertation? That is the plan.
So, what was the huge problem he was trying to tackle? You gotta remember, back in the early 90s, the web was basically the Wild West. It was this chaotic tangle of different systems, all trying to talk to each other, and it was growing at this explosive, totally unpredictable rate. It needed a design, a blueprint that could handle what the dissertation calls internet-scale growth.
And he lays out the challenge really clearly. How do you design for, and I love this phrase, an archic scalability? I mean, how do you build something that can grow like crazy without a central boss telling everyone what to do? It also needed independent deployment. That just means anyone, anywhere should be able to fire up a new website or build a new browser without, breaking the entire internet for everyone else. And on top of all that, it had to work on the slow, clunky, high-latency networks of the early 90s. A pretty tall order.
Okay, so to tackle a problem this big, Fielding knew he needed to define his toolkit first. It's like before you build a house, you need to know what a hammer is, what a nail is, what a wall is. He created this common language, a shared vocabulary, so everyone could be on the same page when talking about network architecture. Let's break down the key parts.
All right, first up, components. Super simple. These are just the actors in the play. Your web browser, that's a component. The Google server it's talking to, that's another component. They're the pieces of software that are actually, doing stuff.
Okay, so if you have actors, you need a way for them to talk to each other, right? That's where connectors come in. They're the communication lines, the pathways. Think of them as the script or the rules of engagement that the actors have to follow. A perfect example of a connector is HTTP, the protocol the whole web uses to communicate.
And then you have the datum. Fancy word, but it just means the data. It's the stuff that's being sent back and forth. The actual HTML for a web page, a picture of a cat, a video, whatever. And this is a really important point. In this architectural model, the data itself is a first-class citizen. It's just as crucial as the components that are sending and receiving it.
And that brings us to the most important concept in the whole dissertation, the architectural style. The best way to think about this is like a recipe for a cake. It's a named set of rules or constraints. If you follow the recipe for a chocolate cake, you get a chocolate cake. You don't get a salad. And if you follow a specific architectural style, you're guaranteed to get a system with certain properties, like being super scalable or really reliable.
So before he just went and invented a whole new recipe from scratch, Fielding did his due diligence. He looked at all the existing architectural styles out there to see if maybe, just maybe, one of them was already good enough for the job of building the web. He checked out styles like pipe and filter, which is great if you're just processing a stream of data, but pretty awful for anything interactive like, clicking a link. The classic client-server model? A decent starting point, but way too basic. Other styles he looked at were just too rigid, too tightly coupled. They would have snapped under the pressure of internet-scale growth. So the big takeaway here was clear. None of the existing blueprints were going to cut it.
So what do? You have to make your own. And this, right here, is where the genius of his work really shines. He didn't just pull a new style out of thin air and say, here it is. No, he built it, step by step. He started with nothing and logically added one rule, one constraint at a time, explaining exactly why each one was so important.
He literally starts with a blank slate. He calls it the null style, basically a system with no rules at all, total chaos. And from there, he starts adding some order.
Okay, so watch how this builds. First, he adds the client-server constraint. Boom. Right away, you get separation of concerns. The user interface over here, the data storage over there. Simple, but huge. Then he adds stateless. This is a game changer. It means the server doesn't have to remember anything about the client from one request to the next. Every request is a fresh start.
Why does that matter? It makes things way more scalable and reliable. Next up, cache. This one's easy to get. It just lets different parts of the system save and reuse common answers, which cuts down on network traffic and makes everything feel faster. Okay, now for the big one, the real masterstroke, the uniform interface. This constraint forces every single part of the system to talk to each other in the exact same way. It creates a universal language, which is what allows the web to be so ridiculously massive, yet fundamentally simple. And finally, he adds the layered system constraint. This allows you to stick things in the middle, like firewalls or proxies, without the client or server even knowing they're there. Great for security, great for load balancing.
And that's it. You take those 5 constraints, you layer them on top of each other, and what you get is the architectural style known as REST, Representational State Transfer. That is the secret blueprint of the modern web.
Okay, so that's all pretty abstract, right? Constraints, styles, components, cool. But how does this academic theory actually connect to me, right now, using the internet?
Well, this really shows you the before and after. Before this REST way of thinking, building network apps was chaos. Every single application had its own weird custom protocol. Things were brittle, they broke all the time, and they were impossible to scale. After REST, we have one single standardized interface for everything. It's designed from the ground up to let different pieces evolve on their own and to scale up to, well, the entire planet.
And you literally see these REST principles in action every single second you're online. Remember that super important uniform interface constraint? Well, what is it? It's the stuff you use every day. It's URIs, web addresses. It's HTTP, the protocol that is the language of the web. It's those standard verbs like get, post, put, and delete. Even the simple, humble hyperlink, that's a core piece of the REST engine.
And here is the absolute best part of the whole story, the kicker. Roy Fielding wasn't just some academic, writing theories from an ivory tower. He was one of the principal authors of the very standards he was talking about in his dissertation. We're talking HTTP/1.1 and the URI standard. So he didn't just draw the blueprint, he then went to the construction site and helped build the whole damn thing. So when you think about it, the fact that the web works at all, that it's so massive and resilient, it's not an accident, it's not magic. It's the result of this incredibly elegant and surprisingly simple blueprint, this set of constraints laid out all those years ago. REST has been, well, widely successful to say the least. And that leaves us with one final, really big question to chew on. If this is the architecture that got us through the first few decades of the internet, what's the blueprint that's going to get us through the next 100 years?